If you have a hot cup of coffee and you let it rest, it's going to cool down on its own. But why does it never heat back up naturally? And how come you can mix up salt and pepper, but you can never unmix them? That's entropy, and it might be the most important reason the universe makes sense. So what is this special entropy? I'll spell it out for you. It's a fancy word for disorder. So imagine a room with clean clothes. This is your room and these are your clean clothes and they're all stacked nice and neat. Now, when you toss these clothes in the air, like that, suddenly it's not neat anymore. This is disorder. The energy didn't disappear. You have the same amount of clothes in your room. However, it got less usable. Entropy measures how spread out and unusable your energy becomes. So there's a special formula for it, which is also on the free cheat sheet in the description. It's famous. It's this. And let's look at each part. Entropy equals the heat that's added to your system divided by the temperature it's added at. Let's say you have a cube of ice and you melt it at 0 degrees Celsius. You're adding heat, but the temperature stays the same. So all of the heat energy that you're adding is going toward breaking bonds so that it can change phase from solid to liquid. It doesn't go toward adding temperature. So if temperature stays the same, but if heat is getting more and more because you're adding more and more heat, then higher disorder. That's entropy in action. Here's a way to imagine it with the formula. Imagine 28 grams of ice and it's melting at 0 degrees Celsius. And there's a formula to find the amount of heat you need to add to change phase. So to change from a solid to a liquid, for example, or ice to water in this case. The heat added is equal to the mass times latent heat constant, which in this case is 333,000 since we're doing water solid to liquid. This is 0.028 times 333,000. This gives us 9,324 joules. 0 degrees Celsius converted to Kelvin, well, we just have to add 273. So this is equal to 273 Kelvin. Now, let's find the entropy, or the amount of disorder. Because we have these two values here. The amount of heat we added to the system is 9,324 joules, and the amount of temperature we're adding it at is 273. This is roughly 34.2 joules per Kelvin, which is a boost in entropy. The energy got more spread out after the ice changed phase. After we added the heat, it's more disordered. But what if the temperature changes? So you can't use this basic formula. Instead, an easy way to do it is to use the average temperature. Let's go through an example problem for entropy. You have a bowl, and inside this bowl, you mix 50 grams of hot water and 50 grams of cold water. The hot water is initially 24 degrees Celsius and the cold water is initially 20 degrees Celsius. Because of how heat works, and if you leave this by itself, they're going to eventually settle at thermal equilibrium and they're going to mix and reach together a temperature of 22 degrees Celsius. So what happens to the entropy here? There's 50 grams of each water, by the way. First of all, we have to find how much energy was lost, because look at the entropy formula. It involves how much heat was added or released. And of course, all the formulas we'll use in this video are in the free cheat sheet in the description. This needs Q. What's Q? Well, there's a formula for it from back in earlier thermodynamics. Which is mass times the specific heat capacity of your thing, which in this case is water, times the change in temperature. Let's start with the hot water. The hot water has a change in temperature of negative 2 degrees Celsius because it went from 24 to 22. This means that we can sub in our values 50 grams of mass. The specific heat capacity of water is 4186 and the change in temperature was 2. So it's 418600 joules of energy or heat that was lost. We can plug this into the entropy formula. So negative 418,600 joules. How about the average temperature? Because remember, we're using average temperature now, and it's in Kelvin. However, the average temperature is not 22 degrees, because we're considering the hot water and the cold water. We use the average temperature for whatever part of the process we're looking at. So we treat them separately because entropy is a path-dependent quantity when temperature changes, which basically means cold water, hot water, we solve it separately. The average temperature for the hot water is between 24 and 22, so 23 degrees Celsius. To convert it to Kelvin, we add 273, which gives us 296 Kelvin on average. put it into the formula, and your answer is this. Negative 1414 joules per Kelvin approximately for the change in entropy. It's negative because it cooled down. So we lost energy, but how about we take a look at the cold water as well, because that's going to tell us some important stuff. The cold water has an average temperature of 22 plus 20 over 2, which is 21 degrees, right in the middle. So the average temperature throughout its heating process. Just like how we took the average temperature throughout the cooling process for the hot water. We put it into the same formula. And since it's water and it weighs the same, the energy gain is also the same as the hot water, 418,600 joules. We put in our 21 degrees Celsius, but we have to convert it to Kelvin by adding 273, which gives us 294 Kelvin. Plug that in, 294. Now the entropy is plus 1424 joules per Kelvin. You might say, oh, this is the same. No, the hot water lost this much. So there's a 10 difference. There's a plus 10 entropy increase. So even though one side lost energy, the overall disorder increased. How about the second law of thermodynamics? I did make a quick introduction video on it. That was in words and it was very conceptual. Here's one that's related to entropy. Because now that you understand entropy, I can reveal the true second law of thermodynamics. In any natural process, entropy in total must increase. So if you mix two waters, the entropy in total must increase. If you let a warm object cool, entropy must increase. If you burn fuel to move, entropy increases. This is why we can't build a 100% efficient engine. You can't unmix your coffee and the universe is always moving toward more disorder. Entropy gives us a direction for time. Here's a bonus visual to help you understand entropy, just to wrap things up. You have all the gas molecules in one corner bunched up. There's low entropy. But if you let them loose and go crazy and they spread everywhere, even if it's the same amount of gas, this is higher entropy. The more ways something can be arranged, the more entropy it has. It's not about chaos, it's about probability. And things move toward disorder because that's what usually just happens. That's why you'll never see your coffee unmix.